Find the volume that would be created by revolving the cross-sectional area shown around the y-axis. I'm going to start with a three-dimensional drawing of the volume that I want to integrate. We're going to take that cross section now and create circles around the Y, spinning a full 360 degrees. This is going to make a swimming pool shaped cylinder that would look something like that. Now we're going to use the disc or washer method to solve this problem. So we want to slice our object up. And the best way to slice it up here, to use the disc method, would be to create sort of pancakes. Pancake-shaped discs. It would look something like that. Okay, now as I had done in a previous video, we want to find one line that is important to these shapes. And that line would be the radius of the discs. And I'll call it R. Let's go ahead and draw that radius on the cross section as well. There it is. Now our boundary is x equals 8 here, and we'd like to turn that into function notation just for a moment. So instead of calling it x equals 8, I'll call it f of y equals 8. So f of y just means we can plug in any given y value here on the y-axis, and then the formula would tell us how large of a horizontal strip we have. In this case, it's just a constant 8. So it doesn't depend on where we're located, which makes this an easy one to do. But it's still a little tricky because we are cutting the object up along the y-axis now, and so our height of it is going to be dy. In my previous video, I had used dx. If we want, we can say that r is a function of y. Whatever y we're at, the radius is 8. I don't have to put the parentheses y there. This is just a constant for all disks. It's going to be the same, so I could just put r equals 8. Keep it simple. What other quantities describe this slice? It has a volume, dV, and the slice has a volume dV. It also has a surface area, which I'll call A. And there's a height dy. Let's give a formula for A. Now the surface area could be a function of y in some problems. In this case, as in my previous video, the surface area of all the disks is actually going to be constant. They'll all have the same surface area, given by the formula pi times r of y squared. In this case, if we want to just make it look a little simpler, we can take the y's out. They're not necessary. The y's are there just to remind us that area and radius could be a function of y. In this case, we don't need that reminder. Let's plug in the number 8. All right, so every disk will have a surface area of 64 pi. Our next job is to write a formula for dV. And we typically want to start with a known geometry formula that we know from our past that we have. And we typically want to start with a geometry formula that we know from our past that the volume of a cylinder is pi r squared h. Taking a differential of both sides, we would get that. And so let's use that. There's also the formula so we want to start with a geometry formula that we know from our past. The volume of a cylinder could be pi r squared h, or sometimes written as V equals A times h, where A is the surface area. Then we could use a differential on both sides to get that differential relationship. And that's what we want to use. But I'll substitute in the 64 pi in place of the A. Now that I have an expression for the volume of this infinitely thin disk, I'll want to integrate both sides. Integrate both sides. So the total volume is going to be an integral of 64 pi dy. I'm going to change dh to dy. dh was the height of our cylinder, but dy actually references our axes, so it's better. Next, since we're cutting it up along the y-axis this time into thin pancake-like disks, our limits should be y as well. We'll go from y equals 0 to y equals 4. So we get this. That gives us 64 pi y from 0 to 4. Which is going to be 256 pi. That's our answer. Now we can check that real quick with the formula from geometry. And let's see, we would get pi times 8 squared times 4, and it checks.